Hi everyone, so the goal of this video is to understand the force of friction. So your learning target is to explain the force of friction and how it affects motion, explain static and kinetic friction, and calculate the force of friction. So before we start, as usual, find a good spot in the classroom so you can watch the video. Make sure you have the guided notes, and the use of headphones is suggested. Useful tip is that you can change the playback speed of this video if I'm talking too fast or talking too slow. Go to the settings in the bottom right and change the playback speed. All right, so this is a little GIF here of Steph Curry, and the question is, how is this related to friction? So you can watch it a couple times and maybe even pause the video to try to think about how is this related to friction. So what is friction? Well, friction is a force that resists the motion of one object moving against another. And I have many examples here, and I'm sure you can think of many other examples in the real world, but a book sliding across the table. Now, up until now, we've only been talking about the force that makes an object move, but we haven't talked about the force that resists that motion. And friction is one of the major motions, or one of the major forces that resists motion. So a book sliding across the table, a box sliding across the floor, a basketball player's sneakers while they run, or a syringe plunger sliding in a barrel. Now, those last two are examples where friction is actually pretty useful. When you're running down the court, it's good to have a lot of friction, right? And you can see some basketball players will even make sure that the bottom of their shoes are a little bit sticky to increase friction, or they'll like take their sweat and they'll rub it on the bottom of their sneakers real quick to kind of increase the friction on their shoes so they don't slip. So in some cases, friction is good. And this is a diagram that you can see here of some of the major forces acting on an object. And we've talked about applying a force. And if you've gotten this far, you've learned about gravity and normal force. And now we're adding this component of the force of friction, which is opposite or in the opposite direction as the force being applied. So what really causes friction? So when two surfaces slide past each other, the two surfaces have many microscopic interactions. So if you zoomed in to look at what's going on those two surfaces sliding past each other, they could be a little bit bumpy, they could have some molecular interactions, and that could increase friction. Now, some surfaces have very few interactions and they slide very easily. Like ice is a really good example. Ice is relatively smooth and it doesn't really interact with the objects that are sliding on it, so things slide very easily on the ice. Others have many interactions and don't slide past each other very easily. A really good example of this is a rubber tire on a concrete surface. That's actually a place where you want to have a lot of friction. You don't want your tires slipping on the road. You want to have a lot of friction and you want to have those tires roll on the road without any slipping. So there are two major types of friction. There's static friction and kinetic friction. So with static friction, you have friction between stationary objects, and you have kinetic friction, which is the friction between moving objects. All right, so I have two pictures here that you could take a look at and see how those two things are different. So in these two pictures, we have static friction on the left, and then we have kinetic friction on the right. So when you look at static friction, you can see that there's a frictional force that's directly opposite to the applied force. Those two forces are equal and opposite, and so that the sum of forces is still zero. Your net force is still zero. So this object is stationary, and we could say that it's experiencing static friction. Now, once you're able to push hard enough to get the object to move, then you're dealing with kinetic friction. And so that's what you can see in this second picture, where we're applying a little bit more force, and now we're applying more force than the frictional force. So now the sum of forces, or the net force, is greater than zero. We're actually going to get this object to move. And so when you look at static friction and kinetic friction, as you apply a force and the object doesn't move, then you're dealing with static friction. So when we look at this graph, what we're kind of looking at here is if you apply a little force, you have some friction. And you apply more force and you still have more friction. And you apply more force and you still have friction. and the friction is kind of increasing until it reaches a threshold. It reaches a threshold where you've actually applied enough force to get the object to move. And then after you reach that threshold, the force kind of drops down and becomes a constant. And so no matter how hard you push, once you get it moving, the kinetic friction is going to be constant. So this kind of, I put this question here, like if you ever notice that something is easier to push once you get it moving, that's exactly what we're dealing with here between static friction and kinetic friction. All right, so this is a very busy chart, and you definitely don't have to know, you don't have to know all of these, but I do just want to point out a couple of things. So I have a couple of questions on the right side, and I'll get to those in a minute. But when you look at this chart, basically what we're looking at here are the coefficients of friction. So coefficient of friction kind of tells you how much friction is there between two different surfaces. So maybe I'll point out a couple that you might be familiar with. Let's see. So how about rubber on concrete? We talked about this one where a tire is on concrete. We want rubber tires on concrete to have very high friction. And this is actually one of the highest ones that you will see on this chart, or really anywhere in the world. I'll point out maybe another one that I think is interesting. So Teflon. Teflon is a material that's on a lot of frying pans. And so if you have ever cooked with a frying pan that's like coated with black, like a black surface, that's probably Teflon. And it makes surfaces very smooth and it makes it hard for things to kind of stick to it. So that number is really, really low. In general, the higher the number, the more friction there is. The lower the number, the less friction there is. And then one other key idea I'll point out here is that notice that this has a little s next to it, and then this has a little k next to it. So this is the coefficient of friction for static, and then this is the coefficient of friction for kinetic. So we would say that this is the kinetic coefficient of friction, and then this is the static coefficient of friction. And notice that in general, the kinetic is lower than the static. So if you went all the way down this column, for just about every number here, the kinetic number is lower than the static number. Kind of getting back to that idea of when you push an object, once you get it moving, it's easy to kind of keep it moving. And that's directly related to the physics of friction. All right, so here are my questions. Which example on the chart has the highest coefficient, and why would that be good? Also, which example has the lowest coefficient, and why would that be good? I suggest pausing the video, taking a look at the chart, and trying to answer those questions. All right, so how do we find the force of friction? How do we actually calculate the force of friction? So this is our equation. We take the force of friction is equal to the normal force times the coefficient of friction. And remember, the normal force is really just depending on like the mass of the object and on gravity. So we'll go over like a couple of examples really quickly here. All right, so a 30 kilogram box is being pushed and it's sliding down the hall. The coefficient of friction, UK, is 0.4. Draw a free body diagram and find the force of friction. Okay, so what I might do here is I will try to draw a free body diagram. And we've gotten to the point where we can draw many forces acting on this object. Now we said it's being pushed, so we know that there's an applied force, so I'll draw an arrow for that. But we also know that there's a force of friction, so we'll draw an arrow for that. We also know that there's a force of gravity, so I'll draw an arrow for that. And there is a normal force that's going to be equal and opposite to gravity, so I'll draw that. Okay, so our free body diagram would look something like this. Now to actually calculate the force of friction, first we need to find the normal force. So I'm going to write a few things down here. I know that the mass is equal to 30 kilograms. And one thing that's not mentioned here is the force of gravity. But if you did well on the gravity lesson, then you might remember that gravity is equal to negative 9.8 meters per second squared. And so if I know the mass and I know gravity, then I can find the force of gravity. That's going to be equal to 30 times negative 9.8. All right, and that is going to be equal to, let me get my calculator really quickly. So we have to do 30 times 9.8. So it's 294. So negative 294. Now we said that the normal force is equal and opposite to the force of gravity. So that would be just positive 294. So now I know my normal force. And I know that the force of friction is my normal force times the coefficient of friction. So now I can find the force of friction by doing the normal force, 294, times 0.4. So the force of friction, final number is 117.6 newtons. So that's my final answer right there. 117.6 newtons. All right. So you need to know the normal force, and you can do that if you know gravity. And then you take your normal force and you multiply it by the coefficient of friction. All right. So you'll probably have some practice problems to do related to this concept. So good luck with those.